While you're at home enjoying your wonderful snow day, I'm here teaching to an empty classroom with the light turned off so that you can see the screen very easily. We've been dealing with derivatives. Today we're going to look at more complex functions that can use something called the chain rule. When you think of a chain, there's multiple pieces. Same thing with this type of function. So we're going to take the derivative of an outside function multiplied by the derivative of an inside function. So for example, let's say our function is f of x equals x squared plus 2 all squared. Yes, we could expand it, or we could write it out 2 times and use the product rule, but as this gets more and more complicated, things are going to get more and more complicated. So this right here, we can make a statement. Let u equal x squared plus 2. When we do that, we then have f of u equals u squared. We know how to take the derivative of that very, very easily. So, without further ado, let's look at some examples. So, our first example here. So we're going to solve this using the chain rule. F of x equals 3x minus 5. So let's start. We have let u equal 3x minus 5. So now I'm going to rewrite that. F of u equals u to the power of 4. When we want to take the derivative of this overall function, so I have f prime of x, we have to start with the derivative of the outside function, and that's the power of the 4, or power of 4. So we're going to work our way in. So I'm going to do the derivative of u, the derivative of f of u with respect to u multiplied by the derivative of u with respect to x. So what does that look like? So we're going to take the derivative of u to the 4 with respect to u times the derivative of 3x minus 5 with respect to x. So this becomes 4u cubed, so I use my power rule, multiplied by the derivative of 3x5. So that's going to be 3x, or sorry, just 3. So then we end up with 12, but instead of writing u cubed, I'm going to replace that with 3x5 to the power of 3. All the examples we had done up to this point, whenever we had an outside exponent, we didn't actually show this chain rule, even though we were actually doing it. All of the examples I picked, the coefficient in front of the x term was always 1. So if we multiply something by 1, it doesn't change it. Now I know some of you don't like the Leibniz notation, so the next example I'm going to do it using Leibniz, and using just normal notation. Alright, so in this example, we are dealing with f of x equals 4 minus x squared to the half. So as I said, I'm going to do it 2 ways. So the first thing I'm going to do is I'm going to make my let statement. Let u be represented by 4 minus x squared. So then I'm going to have f of u is equal to u to the power of 1/2. And our derivative, f prime of x, because that's our ultimate goal, is to have it in terms of x. So I'm going to take the derivative of u to the half dx multiplied by the derivative of u . Let me fix this. The wrong notation there. So I have the derivative of f of u with respect to u times the derivative of u with respect to x. So now I'm actually going to plug in the function. So this here is going to become 1/2 u to the negative half multiplied by the derivative of this bracket right here is going to be minus 2x. Again, we don't like having u and we don't like having negative exponents. So this is really half times 4 minus x squared to the negative 1/2 multiplied by negative 2x. So now when I simplify this here, when I multiply half and the negative 2x, I'm left with negative x. So this is negative x over 4 minus x squared. So when you look at this example, you'll notice that root becomes the denominator because of the negative exponent. Really all I'm doing is I'm sort of looking at the function and treating it as outside working to the inside. All right, now I'm going to do the exact same thing without that Leibniz notation. So I'm starting from the original function. So I have 4 minus x squared to the power of 1/2. So f prime of x. The first thing that I'm going to do is deal with that outside exponent. So I'm going to have 1/2 times 4 minus x squared to the negative 1/2 multiplied by the derivative of the inside. When I do that, I get negative x over root 4 minus x squared. Once you wrap your head around the chain rule, a lot fewer steps can happen, most definitely. This here is sort of explaining that whole function within a function, that composite function once again, whenever we have an outside exponent. Try one or two using Leibniz, where you're explicitly showing the outside, and eventually migrate to an example like this here. I'm not going to simplify this anymore because that's as simple as I get it. Rationalizing, there's no advantage to that at this point. All right, now this one here, when I look at it, let's use the quotient rule. Now, before I do that, I'm going to have y equals 5 over 2 plus bracket 3x squared minus 4. So that's my denominator. So when I do the quotient rule, I have y prime equals the derivative of the numerator. So the derivative of 5 is 0 multiplied by the denominator minus the numerator, which is 5, times the derivative of the denominator. So we look at it, the first number we encounter in the denominator is 2, the derivative of 2 is 0. I just realized I forgot a 1/2 right here. So then when I take the derivative of that, I'm looking outside. So that outside exponent comes down. So I have 1/2, bracket unchanged, to the negative 1/2, multiplied by 6x. And I have that 6x because that's the derivative of the inside bracket. All over 2 plus 3x squared minus 4 to the power of 1/2, and the whole thing is squared. This first term goes away because we're multiplying it by 0. So I'm using the bracket here. Now, over on the other side, when I simplify, I have negative 5 times half times 6x. So that's going to end up giving me negative 15x bracket 3x squared minus 4 to the negative 1/2 all over our denominator. We have one last cleanup step here that we can do. So that power of 1/2 can go down. So I have negative 15x all over bracket 2 plus 3x squared minus 4 to the 1/2 squared. It's very tempting to want to put this squared in to undo this half, but we can't do that because it is plus 2 over there. So that's preventing us. This is as far as we can simplify this expression. All right, next example. So here, getting even more complicated, because now we have multiple exponents and two brackets. So your first cue, you see two things being multiplied, you need to go to the product rule. Then to execute the product rule, there's going to be some steps in between. So let's look at what's happening here. So y prime equals the derivative of the first. So I'm looking at this bracket right here, that r plus 5 to the power of 2. First step, exponent comes down. Multiplied by the bracket unchanged to the power of 1. Then the derivative of the inside bracket is 1 times that r squared minus 5 to the power of 7. Plus, now I'm going to do the exact same thing, but it's the second bracket that I'm going to take the derivative of. So I'm going to have 7 times r squared minus 5 to the power of 6 times 2r, because that's the derivative of r squared minus 5. And then I'm going to multiply it by the first unchanged. So now we notice there are several things that are common. So the number 2 is common. R plus 5 to the power of 1, that's common to both of them. R squared minus 5 to the power of 6, that's also common to both of them. So when I factor that out and I compare, in that first term, I had a 2, I factored it out. I had r plus 5 to the 1, I factored out r plus 5 to the 1. All that's going to be left is r squared minus 5. I had 7 of them, I factored out 6, that leaves me with 1. Now I'm going to move on to the second term. So in this example, there was a 2r, I'm factoring out the 2, so the 2 goes away. So we're left with 7r. There's going to be an r plus 5, and the r squared minus 5 to the 6, that's been factored out. So we have a simplifying step at this point. So this becomes r squared minus 5 plus 7r squared plus 35r. So our very final answer that gives us our final answer. So now the functions we can use are going to be a little bit more complicated. So that's the power rule, product rule, and chain rule all in one. Alright, so this next example, we see a quotient, but we have an overall outside exponent. So when we work this one out, same idea, f prime of x, I'm going to deal with that 4 first. So the 4 comes down in front, 3x plus 1 over 2x minus 1 all cubed. So that's the outside. That is because of the exponent 4. Now on the inside, I have to do the quotient rule. So the derivative of the top is 3 times 2x minus 1 minus the derivative of the bottom times the top all over 2x minus 1 all squared. Now when we simplify this, I'm going to have 4 times 3x plus 1 cubed. Here we're going to have 6x minus 3 minus 6x minus 2. And then I have two 2x minus 1s here. I have 3 over here to give me a total of 2x minus 1 to the power of 5. So our final answer, the 6x's are going to go away. I'm going to have minus 5. So we have minus 20 times 3x plus 1 cubed all over 2x minus 1 to the power of 5. So this should make sense because we had a degree of 4 in the denominator. Now we have a degree of 5. Sometimes students ask, well, Miss, could I change this function to f of x equals 3x plus 1 to the power of 4 over 2x minus 1 to the power of 4, and then just go straight to the quotient rule? The answer is yes. You'll come to the same answer. Whatever works. So if you want, you can go ahead and try it, knowing that this has to be the final answer that you get. All right, so this is probably the last example. Just going to check. Yes, this one here. So the very first thing we're going to do is rewrite it. So we have the root disappear. So from here, I'm going to start off with the quotient rule, because there's no outside exponent that's impacting both the numerator and denominator. So we have y prime equals, the derivative of the numerator is 5 multiplied by 3x minus 4x to the power of half, minus, so the denominator for the derivative of the denominator will be 1/2 bracket 3 minus 4x to the negative 1/2 multiplied by negative 4, because the inside bracket here is negative 4. After you bring down that exponent, you have to do the derivative of the inside. And then I have one more part here. I need that numerator. And then this is all over the denominator squared. Now if we look up top, we have some common things. Actually, there's only really one common thing. And that's going to be 3 minus 4x to the negative half. And we're taking that negative half because we always want the smallest power. So from there, I'm going to have 5. When we divide 3 minus 4x to the 1/2 by 3 minus 4x to the negative half, we're left with 3 minus 4x. Over here, I can multiply the half with the negative 4. So that's going to become plus 2 bracket 5x plus 1. And then 3x minus 4x to the negative half has been factored out, so I don't have that anymore. And then down here, I am allowed to multiply the half and the 2 together to give me 3 minus 4x. From here, now we can simplify. These are like terms. So I can move that negative half down, and then in the numerator, we'll have 15 minus 20x plus 10x plus 2 over 3 minus 4x to the 1/2 times 3 minus 4x. Numerator is going to become negative 10x plus 17 all over 3 minus 4x. Since these are like bases, we can add. Half plus 1 is 3 over 2. So when you look at that, lots of little places where we can make mistakes. But you're going to notice patterns when you're doing this in terms of the factoring, particularly with that negative half. Because whenever you have a root, you're going to end up with a negative half when it's in your numerator. So that is a summary of how to use the chain rule. Monday, when I see you guys again, we will go through a few more examples. I'd like you to start the homework for the chain rule section, so section 2.5, so those questions are there. Monday's class will do a few examples, and then you'll have time to work on these problems. If you have any questions about anything specific, just send me an email. I gave you my email before, marylou.veal@ocsb.ca. I'm here at school until 2:30. So just pop me off an email, and good luck. Enjoy the rest of your snow day.